We can also derive uniform convergence result. This is the proof pretty much the same with the penguin learning analysis. The theorem is this: for any collection hypothesis class H and distribution data distribution D, if a training sample S is drawn from distribution D of size n, which is greater than a over epsilon square log zeta function to n plus log 4 over delta, then with probability greater than 1 minus delta, every hypothesis belong to the hypothesis class will have this epsilon generality, this uniform convergence property. So every hypothesis of which training set and test set difference is n most epsilon. Okay, the proof is pretty much the same. So let S be the set of n random samples according to the data generation process D, probability D, and let define E1 as the event that exists on hypothesis H, such that this is the test error minus this is the training error, the number of data points belong to the hypothesis H over set S, okay, which is greater than epsilon. So that is bad event, and we want to upper bound the probability of bad event by delta. And we want to make the sample complexity is rho bounded by this. So let S prime and S be two independent sample set with size n. And we define E2, another event. Like before, this is kind of double sampling technique. So there exists on hypothesis H such that the generalization error, the difference between training and test is n least epsilon. But for the second set of training point S prime, our training and test and training difference is n most epsilon over 2. Okay, so for the first trial, that was bad. But the second trial, the second collection of data, we have good generalization. Okay, since we add one more condition to define E2, we can easily check that E2 is subset of E1. So when E2 hold, naturally E1 also true. So for given H star, consider E1 star as this. Okay, the event, the training error of the H star has n least epsilon difference with the test error of H star. And also, let's assume the probability of E1 star is strictly greater than 0. Let P is equal to the PDH star, which means when you randomly sample one training data or one data instance from distribution D, the distribution D belongs to the positive label area of H star hypothesis. So when P is equal to 0, then essentially P1 star is null set, because P equal to 0 means whenever you sample, always the sample will located in the negative area. So the training error also always 0, test error also 0 from the definition. So therefore, P should be strictly greater than 0. From the definition, the number of data points belong to the positive area in H star when you sample first n data point to define S, and the number of data points belong to the positive area of H star from the next n training data point, which is defined as star. They are independent and both follow the same binomial distribution with parameter n and p. N is the number of trials and p is the probability we get positive response for each trial. And let E2 star like this. The event, the test error of H star minus training error S star by S star is bounded by epsilon over 2. Okay, since S and S prime sampling are independent, E1 star and E2 star also independent. And when n is greater than 4 over epsilon square from the Hefting's inequality, we can check this. Because E1 star and E2 star are independent, the conditional distribution of E2 star for given E1 star, we can ignore E1 star. And the distribution of E2 star is, the probability of E2 star is defined like this, and by Hefting's inequality, this number will concentrate around the expectation NP, and since the variance is always since the outcome will 0 or 1, so which is bounded interval, so we can apply Hefting's inequality and we can simply obtain this result. So from the previous page, since the probability of E2 is n is 1 over 2 independently to the hypothesis probability for all hypotheses S, then can make E1. So basically from the previous page, what we can say is from the definition of E2 star and E1 star, E2 for given E1 is equal to the probability of E2 star given E1 star. From the definition of E2 star, E1 star, E2 and E1, we can simply do this. So we have this from the previous slide. And since PE2 is equal to this Y, E2 is subset of E1. So we can rewrite E2 as E2 and E1 intersection. And from Bayesian rule, we can present E2 and E1 intersection as the product of probability of E1 and probability of E2 given E1. And since this is bounded by 1 over 2, we have this. So PE1, the probability of event 1 is less than 2 times probability of event 2, E2. And in this proof, we want to show that this probability is upper bounded by delta. So to bound this is sufficient. It is sufficient to show that this is upper bounded by delta. So we just need to show that probability of E2 is bounded by delta over 2. Okay, that also fine. Right. So double sampling, what we used last time, we used the independence property of S and S prime. So we first define a subset of E2 as follows. E prime 2, which is equal to, there exists an H set H such that the difference between training error obtained by S and the training error obtained by S prime. Okay, which is greater than or equal to epsilon over 2. Okay, when there exists any hypothesis that having some huge difference between a training error by the first set and training error by the second set, in other words, we can write down this by multiplying the cardinality of S and S prime. They are the same to N. So when the first set and the second set have totally different training error, we can expect this and this both hold. This is very simple trick. When this and this both are true, then the training error by the first set and the training error by the second set will have difference at least epsilon over 2 by definition, right? So E2 prime defined like this based on the fact. We just need to check. So we don't care how much the training error different with the test error. We just focus on the difference between the first set training error, the second training error. And when the difference is bigger than epsilon over 2, then we count. So one can easily check that E2 is subset of E2 prime. So when E2 hold, E2 prime always hold. So for any hypothesis, we define, let's say EH is this. Okay, and then we will apply union bound using the cardinality of hypothesis set that defined on the two n sides of training data point, S and S prime. And the VC dimension will upper bounding the cardinality of hypothesis. So let xi and xi prime be indicator whether the ith instance of S and S prime. Okay, so they are training set, and each training set is generated from our random process or random coin tossing by D. So we can think the training set S and S prime both are sequentially generated from time 1 to time n. So this is x1 and x1 prime, this is x2, x2 prime, up to xn, xn prime. Right. And this value is equal to 1 if the first point, x1, the first point belongs to the positive area, equal to 0 if it belongs to the 0 area. Then the number of samples, the number of positive samples is equal to the sum of random variable. And each random variable indeed a Bernoulli random variable with parameter p from the definition of p. So we can think the difference of number of positive sample of S and number of positive sample of S prime is a sum of IID random variable like this, xi minus xi prime. And let yi be a random variable that is independent to S and S prime, and it has either value 1 or minus 1 with probability 1/2. Then the random variable this essentially equal to this, and since y is just a coin tossing 1 or minus 1, and this random variable is symmetric to the 0, in distribution they are the same. Okay, so therefore when S and S prime are given, this can be considered as sum of random variable, and this random variable having mean 0 and bounded interval. So we can apply Pfeffding's inequality again to find out the probability of E prime H. So from the Pfeffding's inequality, we can bounding the probability of E prime H for given S and S prime. And since S and S prime, each set size is equal to n, so their cardinality always upper bounded by 2n. Why this is not equal to 2n? Because there could be some overlapped data point. that is not important thing. So the number of hypotheses H that make a difference, this is upper bounded by the shelter function like this, and from the union bound in the end we have this, and this make our final result.